Hello all these students. So today we are going to discuss a new topic which is Hasse diagrams. Now before I start with Hasse diagrams, we should know that what are Hasse diagrams. So basically when I talk of a Hasse diagram, that means it is a graph which is a directed graph. So Hasse diagram is always a directed graph. One more thing, why do we use graphs at first place? Because graphs provide you with an easier representation. It is easier to represent a relation using graphs. The graphical representation reduces the complexity. Okay, and one more important thing, that a Hasse diagram is always and only made for relations which are partially ordered, or in other words, you make a Hasse diagram for a poset. Now why do we use directed graphs as Hasse diagrams? Because we know that a relation consists of ordered pairs. A relation always consists of ordered pairs. So to represent them graphically, it's quite obvious that we will use directed graphs only. Okay, now let's start with how to draw a Hasse diagram. If I have a set S which consists of elements 1, 2, 4, 6 and 8, and I have a relation R which is defined on this set, which says that R is a set of ordered pair A and B such that A divides B. Alright, so I have a set which consists of elements 1, 2, 4, 6, 8. Now this relation is always formed on some set. So here in this case, this relation R is formed on the set S. And what is the criteria for the formation of this relation? It says that relation R consists of ordered pairs A and B such that A divides B, or in other words, B is divisible by A, right? So this is the criteria for the formation of the relation, and it's quite obvious that this relation is formed on the set S. Now let us see what all elements we can have in this relation. Okay, so you can see that it consists of ordered pairs A and B, and the criteria for the formation of the relation is that A divides B or B is divisible by A. So what all elements as ordered pairs will we have in this relation? I will have all these elements. First of all, I know that 1 divides 1, then I know 2 divides 2, then I know 4 divides 4, then I know 6 divides 6, I also know 8 divides 8. So first these ordered pairs I have taken. Then I know that 1 divides 2, I know 1 divides 4, I know 1 divides 6, I also know 1 divides 8, right? Then I know that 2 divides 4, 2 divides 6 and 2 divides 8, right? Then I know that 4 divides 8, right? 6 cannot divide 8 because it is not completely divisible. Alright, so these are the total number of ordered pairs that I have in this relationship which satisfy my criteria that A is divisible by B. So in the ordered pair, if I represent it as A and B, then the first element is A and the second element is B, and my criteria is that A divides B, that is the first element divides the second element. Okay, now as I told you, a Hasse diagram is always made on a poset or a relation which is partially ordered, right? So what is a partially ordered relation? I know that it is always reflexive. Yes, it is always transitive. It is always anti-symmetric. Yes or no? Yes, a poset will have all these three qualities. It will be reflexive, it will be anti-symmetric, and it will be transitive. Okay, now let's see if it is reflexive or not. To be reflexive, it must have the ordered pair A comma A for all the elements of the set. Now the elements of the set are 1, 2, 4, 6, 8. So according to this definition, I must have ordered pair 1 comma 1, 2 comma 2, 4 comma 4, 6 comma 6, and 8 comma 8, which I am having. So yes, it is reflexive for sure. Then let's see if it is anti-symmetric or not. Now I know to be anti-symmetric, if A comma B exists in the relation, then B comma A must not exist in this relation. And if B comma A exists, then in that case A must be equal to B. So either if A comma B exists, then B comma A must not exist, and if B comma A exists, then A must be equal to B. So let us see if it is antisymmetric or not. Now I have ordered pair 1, 2, but 2, 1 is not existing anywhere. I have 1, 4, 4, 1 is not existing anywhere. 1, 6, 6, 1 is not existing anywhere. 1, 8, can you see 8, 1 anywhere? No. 2, 4, can you see 4, 2 anywhere? No. 2, 6, 6, 2 is not here. 2, 8, 8, 2 is not here. 4, 8, 8, 4 is not here. So it's anti-symmetric for sure, because for all the pairs which exist in the form of A comma B, a BA does not exist. Alright, so that means we know that this relation is reflexive and antisymmetric by far. Now let us see if it is transitive or not. I know to be transitive, if A divides B, then, and if B divides C, then A must divide C. Yes, if A divides B and if B divides C, then obviously A will divide C, because if 1 divides 2 and if 2 divides 4, then it's quite obvious that 1 will divide 4. So that means it is transitive also. Now since it is reflexive also, it is antisymmetric also, and it is transitive also, so I can say that it is a partially ordered relation. Okay, now since it is a partially ordered relation, that means I can draw a Hasse diagram for this relation, because I told you in the beginning that a Hasse diagram is only drawn for a poset or a partially ordered relation. So now since we have proved that this is a partially ordered relation, so we can go ahead and draw a Hasse diagram for it. Okay, now if I draw a graph of this relation, I know that all the elements of the relation represent the vertices of the graph. So I have, first of all, I'll copy down all the elements of the set. Now what are all these elements? 1, 2, 4, 6, 8. So I will randomly put them like this: 1, 2, 4, 6 and 8. Okay, so all the elements are represented by the vertices of the graph. So this is one vertex, second vertex, third, fourth and fifth. So the first step is that all the elements of the set, I will put them like this as vertices of the graph. Now the next step is to see which all elements exist in the ordered pair or which all elements are related to each other. Now, since I know that this is a partially ordered relation, so it is quite obvious that it will be reflexive. And since it is reflexive, that means all the elements will be related to themselves. So there will be a self loop. Like here, 1 is related to 1. Then 2 is related to 2. 4 is related to 4. Then 6 is related to 6. And 8 is related to 8. It's quite obvious because because it is reflexive. So there will be self loop. Alright. Now this part is done. Then I can see that 1 is related to 2. So an arrow goes from 1 to 2. Right? Then 1 is related to 4. So 1, 2, 4. Clear? Now 1 is related to 6. Then 1 is related to 8. Fine? And then 2 is related to 4. Then 2 is related to 6. Then 2 is related to 8. And 4 is related to 8. So this is my directed graph for this relation. Now I will rub this, since I hope that you must have copied the elements or the ordered pairs of the relation. So this is my graph for this relation. Now to convert it into a Hasse diagram, the first step is that remove the self loops. Remove all the self loops in the directed graph, because I know that this is a partially ordered relation and it is quite obvious that a partially ordered relation will have self loops. So I do not need to show them specifically. So I will erase all the or remove all the self loops. So the first step that I do is that I remove all the self loops, because it is quite obvious that it is a poset and so it is reflexive, so it will have self loops by default. So the first step is that I have removed all these self loops from my graph. Okay, now the next step is to remove all the transitive edges, right? Transitive edges means if there is an edge from 1 to 2 and there is an edge from 2 to 4. So it is quite obvious that there will be an edge from 1 to 4 also. Because if 1 divides 2 and 2 divides 4, then it is quite obvious then 1 will divide 4 also. So for a poset or a partially ordered relation, I know that it is quite obvious that it will be transitive also. So again, I do not need to specifically show the transitive edges. So I will remove all the transitive edges. If 1 divides 6 and 6 divides 8, so it is quite obvious that 1 divides 8 also, right? Similarly, if 2 divides 4 and 4 divides 8, it is quite obvious that 2 will divide 8 also. So here you can see I have removed all the transitive edges, right? So this has become even more simpler now. And the last step says that remove the directed edges. Remove all the directed edges and make simple non-directed edges. Generally in the relation it goes from top to bottom. So it is quite clear that if there is a relation between 1 and 2, so the order would be from 1 to 2. Similarly, if it goes from 2 to 4, then it is quite obvious that it will go from 2 to 4. So I will remove all the directed arrows and make it undirected. So like this it goes. So even when there are no directed arrows, I can tell the direction of the edges because it is a relation and it goes from top to bottom. So if there is a relation from 1 to 2, it will be from 1 to 2, 2 to 4, 2 to 6, 1 to 6, 1 to 8, right? So now this simplified version of the diagram that I have got after 3 filtrations in these 3 steps is what you call the Hasse diagram. All right. So this you can also write it like this. You can proceed with all the elements in from top to bottom, 1, 2, 4, 6 and 8. So there is an edge from 1 to 2, 2 to 4, 4 to 6 and 2 to 8. So you can draw it this way also. So this is my Hasse diagram. It's very simple, nothing complicated. Now let's see one more example of how we can draw a Hasse diagram. We will see one more problem. Okay, now let us assume I have a set which has elements 1, 2, 3 and 4. Alright, so I have a set which is having elements 1, 2, 3 and 4. Then I have a relation which has elements 1, 1, 1, 2, 1, 3, 1, 4, 2, 2, 2, 3, 2, 4, then 3, 3, 3, 4 and 4, 4. So these are all the elements, ordered pairs of my relation. Now I know in advance, or I've been given this thing in advance, that this relation is a partially ordered relation, right? Okay. Now the first step to draw the Hasse diagram is, what will I do? First of all, I will put all the elements of the set in the form of vertices of the graph and in a top to bottom manner. Like 1 comes here, 2, 3, 4. So first of all, I will arrange all the elements in this manner. Now let's see which all elements are related. Of course, without even seeing, I can say that there exists self loops in this graph because it is a Hasse diagram, and Hasse diagram has to be on a partially ordered relation which is always reflexive. So there will be self loops 1 to 1, then 2, then 3, then 4. So these are all these self loops for these elements 1, 1, 2, 2, 3, 3 and 4, 4. And then I can see there's 1 is connected to 2, 1 is connected to 3, 1 is connected to 4. Alright, 1 is connected to 4, then 2 is connected to 3. Alright, then 2 is connected to 4, 3 is connected to 4, and obviously 4 is connected to 4. So this is the final representation of this relation as a graph. Now I will start converting it into a Hasse diagram. So the first step says that remove self loops. So I will remove all these self loops from here. This, then for 2, and then for 4, 1. So all the self loops are now removed for this graph. So doesn't it look simplified and clean now? Yes. Then the next step says remove all the transitive edges. Okay, so if 1 is connected to 2 and 2 is connected to 3, it is quite obvious that 1 will be connected to 3. So remove this transitive edge from 1 to 3, right? Now if 1 is connected to 2, 2 is connected to 3 and 3 is connected to 4. So it is quite obvious that 1 would be connected to 4 also. So remove this transitive edge also from 1 to 4. Now if 2 is connected to 3 and 3 is connected to 4, it is quite obvious that 2 would be connected to 4 also. So remove this transitive edge also, right? So this is how my diagram looks or my graph looks after removing all the transitive edges. Now the third and the last step says remove all the directed arrows, because we know that the relation would go from top to bottom. So I make this as an undirected graph like this. So this simplified version of the graph that I have got after performing these 3 steps is now what you can call the Hasse diagram. So this is all about Hasse diagrams.